Okay. Good morning, everyone. I'm sleepy now. I'd like to talk about the coordinated observations of these satellites. And first of all, before going to the scientific discussion, Bart requested me to talk about the introduction of co-alignment of various instruments, so I tried to do this one. So one important thing in analysis of the time series of data is to remove the drift and to align the multi-wavelength data. So first, let's think about it doesn't work. Think about the first one. This is the iris movie, sit and stare mode in active regions. But did you notice this slit is not stable at single locations, right? This is almost stable, but it's not. And it's hard to see on the keynote, so I go out of this keynote, but I show a quick time player. This is the same movie, and I spun the nose well, I think, but this one is not stable, slightly drifting like this. So such kind of drift can affect the research work. But the maximum drift is 1 nanosecond in 98 minutes, which is one orbit of a satellite. So this is caused by orbital variation that is called wobble. But a large wobble, more than 3 arcseconds, is removed. But residual still remains like this. And I think it is not important for such kind of flare studies, but maybe it's important for wave study because we detect sub-arcsecond oscillations. So we should remove such kind of drift before analysis. So how to do? And I usually use this ideal command, get Corel offsets.pro, developed by Ted Pavel et al. And this is an example movie. This is without program, and this is with program. You can find a clear movie like this. And if you use this program, I recommend you to apply this program to 2 consecutive data and repeat it, not to all data in one time. And also, you should pick up a small field of view, not a large field of view, including a remarkable feature, such kind of bright points. And then you should use, you can use shiftimage.pro. This program can perform a sub-pixel shift. So I like this one. And these processes are not enough. Please try the below ones. For example, change the gamma value. So, for example, square the intensity or smooth images. And also this one is also useful for alignment in time series of data. And I go to the next one. And basically, these procedures can be applied to alignment of various instruments, so different data, I mean. So, and ideally, if we align the first images of each wavelength, all data will be expected to be perfect. But I note that things doesn't always go well. But anyway, yesterday, as Thiago said, If you can use continuum images, use them. That's the best way to alignment. And if you don't, try to align the bright point with less activity. And in such a case, SOT calcium data and also slit 1400. But these bright points on the calcium and silicon slit images are very active, so active that co-alignment often fails. So in such a case, for example, so in such a case, it's better to use AIA 1600 images to align. So, for example, alignment between calcium and 1600, and then between 600 and 1400 in iris data, and combine these. But with this way, the point accuracy is no more than 1 arcsecond because this limits the value. And these are also useful. So please try these procedures. And this is the explanation. So if you are interested in this, please contact me later. Okay. So from now, this is a scientific discussion. This is a coordinated observation of prominence taken on when 2013 October 19th. The yellow one is ISOT calcium movie. And these 4 white lines show the iris slit locations. And these are iris spectra of silicon and magnesium line along these lines. And only with this SOT data, you can find many interesting features. For example, I divided this movie into 2 regions like this. And the lower region has a long thread, small oscillations, and a long lifetime you can find, I think. On the other hand, higher part has opposite characteristics. And also, recently, we have iris data, so we know the line width and the upper region, around the upper region here, so here, has a broader line width. So from this information, we can speculate that the upper region of this prominence is strongly affected by waves, and also we can expect the heating takes place in the upper region of this prominence. So I talk about this one in this talk. And on the other hand, the lower region is discussed in my poster, so please come to my poster about the prominence rotation. So first, I show height variation of physical parameters of this prominence. This is the same image, but rotated. And this white line is iris slit locations from A to B, the lower part to higher part. And the right panels are XT plot, space-time plot along this slit. And then these A and B correspond to this A and this B. And as I said, the higher part of this prominence has a large velocity amplitude and also large line width like this. And to make it clear, I made histograms of these parameters, the line of sight velocity and width. And now I divided this prominence into 4 regions like this. Blue to red correspond to lower height to higher altitude. And you can see the higher region has a larger velocity, more than 20 kilometers per second. And also you can find the line width increases clearly with height. So we think the upper region of this prominence has a strong non-thermal components, and that will expect to heat the plasma. So if heating takes place, we can find something in this movie. So I investigated that. To avoid the line of sight superpositions, I picked up this region, this white green regions, and make a space-time plot like this. The yellow one is a lower temperature taken in the calcium line, and the white one is a silicon line. The horizontal axis is a horizontal position along this, and the vertical one is a time. You can find the cool plasma is moving like this, and then here cool plasma disappears, but the higher temperature plasma appears from here or something like that. And we can find similar things. Well, in particular here, yellow one come here, but disappears, but the white one appears from here strongly. So I think this is evidence of heating in prominence. Okay, so next I focus on the small-scale dynamics of this prominence. So I pick up one fine structure that is called threads, and show a movie of calcium images. And this is original data, and this is emphasized calcium data. And these dotted lines are iris slit locations. And I put one artificial slit here, white vertical slit, to make a space-time plot like this. But this image is negative. This is positive image. So you can find vertical oscillations of this prominent thread as a dark feature like this. And this color indicates the slit locations like this. And this is the velocity at these three positions. And from these panels, we notice that these velocities are in phase over three slit locations. So, but this is much larger than the width of the calcium thread. So this indicates that there is a larger flux tube, but we cannot see it in calcium images. That may be due to opacity effect of magnesium line. This is taken by magnesium line. Okay, and also from this panel again, we can derive two properties. One is changing velocity sign with time, so positive, negative, and positive. But I note that the red one is always positive, but this is because the line of sight components that affect the single Gaussian fitting. And the second one is in phase velocity patterns at two slit locations at green and red, like this. Decreasing and increasing, like this. And also I show another panel. The background image is the same as this one, but I picked up the velocity at the closest slit from the centroid of the thread. And the velocity is plotted as red diamonds. And you can find the transverse oscillation as this yellow one, and the Doppler velocity as a red one has a 180-degree phase difference. That's an interesting point. So let's think about what kind of motions most likely happens in this prominence, in this thread. This is observational facts. The velocity pattern at the top and the bottom of this flux tube is in phase, but the transverse displacement and velocity patterns, these velocities have a antiphase. And I list 3 famous motions in the solar corona, but either of them don't match these observations. So we should consider about more. There's a possibility that we observed a different part of this thread. So far, we thought we see the main body. We observed the main body of this thread, but maybe that's different. So we consider another important information, that is opacity of magnesium lines. Magnesium, according to the radiative transfer, magnesium line has a high opacity. So that means this velocity reflects the surface motion of the thread, like this. This is the simulation data. The right one is the calcium. Calcium is optically thin, so we can see the motion of the entire body. But in magnesium line, we can see only the surface part of the flux tube. This is a cross section of the flux tube. So that velocity is the motion of the surface. So with this information and observational facts, the resonant absorption emerge as a possible solution to explain observational facts. Sorry. Resonant absorption generates triggers azimuthal flows on the surface of the flux tubes, and this is a simulation movie. So please look at this one. We look at the oscillating thread along the axis, and this flux tube is oscillating horizontally this direction, and this horizontal motion triggers the azimuthal flows on the surface. And when we see this oscillating thread from this direction, for example, 45 degrees, and we made synthesized profiles, space-time plots. And this is the intensity, and this is the Doppler velocity, and these 3 colors indicate the iris slit locations, and this is the velocity at these 3 positions. From these panels, this mechanism can explain the observational feature as well. One is the in-phase velocity patterns at 2 slit locations, green and red, for example. So this green and red are in phase. And also changing velocity sign with time, you can see clearly. And also, it's hard to see, but the centroid of the flux tube is plotted as a dashed black line, this one. And first, this black line and color lines have a 90-degree difference, but later, these are anti-phase, or 180-degree phase difference. So this one reproduces observational facts. And such kind of resonance absorption excites Kelvin-Helmholtz instability on the surface of the oscillating flux tube. And such motions produce vortices on the surface. And in the vortices, there are many small current sheets generated, and there they can dissipate the oscillating energy, and finally hit the plasma in the corona. And such kind of heating is also reproduced by this simulation. This is a magnesium line, so 10,000 Kelvin plasma, and this is a silicon image, a synthesized silicon image, and intensity appears after disappearing of magnesium line, like this. That includes question time.
No, that's your.
Okay, but the next is the last slide. So this is a summary. So far, as you know, we observed a lot of waves, in particular propagating waves in the corona, including my work and, for example, Bud, Scott, etc. So, and now we are going to investigation of a dissipation process observationally of such kind of propagating waves. So enjoy the wave studies with IBIS. And I don't know this one, the generation process. Maybe that's future mission. That's difficult to observe. Okay, that's all.
Very clear. Okay, let me ask you a question. If this is resonant absorption, why don't you see the amplitude going down with time?
I don't think the energy input is impulsively, but continuously. So, yes. So, decrease of amplitude and exciting amplitude is simultaneously happened. So, it's hard to see, I think.
Yep.
You have taken one slit at a given location, so do you find the similar behavior at the various other slit positions of the
Other slit positions? Other slit positions, a lot of superpositions along the line of sight, so it's hard to identify a clear oscillations. Maybe we can find, but I show the clearest example.
Denner?
You emphasize the importance of properly co-aligning different data sets.
Mm-hmm.
Why is it that in our community we have to do this ourselves with manually cross-correlating the data file? Why isn't that at mission level done properly so that the header information is correct and you can use simple mapping routines without... Wouldn't it be worth the effort by that NASA funds somebody to do this once and forever, right?
I hope so.
I know it's a lot of manual work, but
right, yes.
you know how many people waste their time trying to...
I spent my half of my time to align the data. Actually, yes. And also, I'm not a NASA person, so please.
I mean, I'm sure that in the astrophysics community, they have the resources and they do this. There's a priority. This has to be done. So this is not something which is everybody.
So as for AIA, yeah. As for AIA, yeah, it's okay, I think. Yeah.
Well, it all depends on what level of precision you want, right? The header information in Hinode, Iris, SDO is pretty accurate down to a certain level, and it depends on the mission. SDO is pretty good, but if you really want to go to subarc second co-alignment, then I think, you know, there's issues there. A lot of it is, like you said, it's a lot of manual work, and it usually requires a lot of, it's not necessarily all automatic, and that makes it not the easiest thing to do. Ted,
okay.
That's what I wanted to provoke, a reply from Ted.
For, in the case of SOT, you can work
I just want
for process the data co-align with AIA the entire SDO period.
introduce a level 1 archive, a new archive.
Yeah, maybe. Oh, okay. It's like this. Okay.
Say we succeed now with this batch processing for something like
There is a laser.
75%. But it's really not.
This one.
Fields of view are so different from one program to another. We haven't given up yet. I think later this year we will have a new archive that has better headers for, like they say, 75% of the data or more, but it's very small.
And similarly for Iris, we're also working, Paul may want to comment if he's here.
I think part of the problem is that
Should work.
you do a batch process.
That's just what it was. Yes, thank you very much.
Mm-hmm. Mm-hmm.
An Irish pixel and an SOG pixel. It's not clear that really is efficient to do it in a complex way. At that point, you're sort of chasing around and every operation.
But I guess in summary, I think there's a lot of work on the instrument team side happening right now to improve the co-alignment. But as Paul is pointing out, down to the last Iris pixel, that's extremely hard to do in an automated fashion, and it's probably not feasible.
What level would you say are the data now for Switzerland? I mean, CDS, ICE, for instance, had offsets of several arcseconds.
I don't know if Sabrina's here today, or she may want to comment. Ted, do you know what the precision? I think actually for ICE, they now do co-alignment with AIA, and they have some routine to improve their pointing.
1 or 2 access is okay.
I mean, ICE now is, the standard for running ICE is that you put in this adjustment file, and it should be better than at least 3, 4, 5 arc seconds.
Okay, so it should be better than 3, 4, 5 arc seconds for ICE. I think for Iris, we are working on the co-alignment, automatic co-alignment with AIA, and I think that should be implemented soon. And then we're down to whatever the AA precision is, which is an arc second maybe or something, maybe 2.
Yeah, it still has some residual variation, even in SDO, that's not very correct. So yeah, our second.
But we are talking also about SDO to, right now SDO is doing the internal co-alignment updates once a week, but we're looking into doing that more frequently because there are drifts on the Iris level. If you want to co-align with SDO, where you do see them drift apart, but you shouldn't just take the SDO co-alignment as a given. So it's work in progress. But there were some other questions for Joten, so Hugh.
So a quick comment about this issue, which is really interesting, and then a question. The comment is that I think there are ways to do this in hardware. There must be ways to do this in hardware because, for example, radio astronomers can calibrate positions to milliarc seconds. Mm-hmm. You have to pay money for it. Space Telescope does this. They have a very elaborate system for very fine co-alignment. So the scientists who are wasting their time doing X and Y calibrations just have to spend more of their time lobbying for that part of the hardware that makes this task easier. So that's my comment. Mm-hmm. The question is about your cartoon. You show the Kelvin-Helmholtz instability setting in as a function of altitude. You're implying you have some ideas about what physical conditions allow this instability and this coupling to occur. So what is your take on where, I mean, people apply this to many domains. So what are the physical parameters that lead to this instability?
I don't have a strong idea, but one possibility is the length of the flux, magnetic flux, magnetic fields. Yeah, for example.
I think your talk is very interesting. I have a question. When you relate the large scale wave to the heating, I think it's still far from to say the contribution to the heating is from the large wave. The reason is large wave have to cascade into small scale and can resonate with the particles. Mm-hmm. So in fact, it's a small fraction of the energy can really contribute to the heating. So do you have any estimation to your current observation how much fraction
I'm here.
contribute
So
to
far,
the
I
heating?
didn't have a quantitative study of this, so I don't have an answer for that. But to investigate that, we need more information, for example, magnetic field strength and density. So maybe large error exists now. So even with Hinode and Iris, I don't think we can do that. The percentage of the...
Yeah, I'm sure the large-scale wave have contribution to the heating.
So
but
this is a
we still, I think still we have to be careful that dominate wave.
Yeah.
Yeah.
Okay, I think we'll have to move on to the next speaker. Thank you again, Joten.
Thank you very much.
And the next speaker is Peter Heinzel, and he's going to talk about solar prominences
I have my.
with Iris.
Morning, everybody. So let's continue with prominences. I will start with a nice movie which was taken by Hinode some years ago. And this shows typical quiescent prominence, heterotype with a lot of magnetic structures and dynamics. You see sort of vertically aligned threads, quasi-threads, which follow what we understand the magnetic dips, complicated magnetic structure, and a lot of dynamics, flows, and so on. So this is something which we want to study also with Iris, and we started with some more simple observations. I will show you some preliminary analysis, radiative transfer modeling, but we are going towards more complex studies, even using Iris of these types of structures. So first spectra of Iris, first light spectra of Iris, they also contained spectrum of such a prominence in magnesium lines. It was taken on the south pole of the sun, and you see this is the limb, this is the chromosphere, this also, and here you see very narrow, practically unreversed profiles, or not profiles but lines, magnesium lines in prominence which is of such a type like quiescent prominences I have shown to you before. So we started some analysis of this spectra, and Jean-Claude Vial will give a talk on this specific event because there is a paper now submitted on that topic. Then we did some modeling of prominences, starting with some more simple structures. We actually continued what we did before for hydrogen lines, especially Lyman lines, which are optically very thick, Lyman alpha, Lyman beta, and so on. For that, we used Sumer observations from SOHO, and we continue this kind of modeling also for magnesium. So there is a paper on this modeling. It's a relatively simple geometry, just illuminated structure, sort of homogeneous slab with temperature structure, pressure structure. What is important ingredient for non-LTE modeling of prominences? It is that all these structures are strongly irradiated from the solar surface. So the boundary conditions to solve the radiative transfer problem, you have to specify very carefully all incident radiations in all transitions, continuum lines, and so on, to get the correct output spectrum. Actually, the problem is that this is, of course, famous transfer equation, very simple in 1D. The problem is that the source function in strong lines like Lyman alpha of hydrogen, magnesium lines, which are also strong resonance lines, calcium lines, the source function is dominated by the scattering term. So the dominant process is the scattering of incident radiation from the photosphere and chromosphere. Actually, this famous parameter epsilon is of the order of 10 to minus 5 for magnesium lines, very small. The previous speaker mentioned the opacity of magnesium lines. The opacity is really large, and it is very interesting because with Iris we can see a lot of structures which we don't see, for example, in H-alpha at all, because H-alpha is more optically thin. Here I show simple table which we produce with these non-LTE transfer calculations. This is the thickness of the structure in kilometers. This is the temperature and gas pressure. You see, this is typical range of gas pressures in prominences, in quiescent prominences. And here you see the line center optical thickness of H-alpha, calcium H, and magnesium H. So you see big differences. If you have, for example, H-alpha of the order of 1, magnesium is already of the order of 70, which is optically very thick. And K-line will be twice more, of course. So this will allow us to see a lot of structures and resolve a lot of structures which are not, for example, visible in H-alpha, or which, if you look at H-alpha, you have strong integration along the line of sight of structures. Then ionization of magnesium is very similar in prominences as in the chromosphere. So here we computed the ionization from magnesium 2 to magnesium 3. You see depends on the temperature, and somewhere between 15,000, 20,000 K, you get almost fully ionized magnesium, so you get magnesium 3. So if we observe magnesium lines, this is, of course, in this temperature range, not at very high temperatures. Then we computed the line profiles. This is magnesium K line for different structures with correct illumination of the structure from the solar surface. For the illumination, we took observed profiles, observations, not theoretical ones. And here you can see variety of profiles. I don't have time to discuss these, but you see some profiles are unreversed for low pressures, low densities, but for higher pressures, you get already a reversal in the line center. Important aspect of these resonance lines is so-called partial distribution scattering, which means that you scatter the photon from the chromosphere, and the scattered photon, which is emitted, has some memory and depends on the frequency and direction of the incoming photon. So this is called in astrophysics the partial distribution in the plasma. For example, for Lyman alpha, we have shown many years ago that it is very critical. This dashed line shows so-called complete redistribution. This is very, very approximate approach. And the correct partial redistribution, which is described by so-called redistribution functions with some branching ratio, which depends on the collisions and densities, you get these two peaks. And this very well fits the observation. So you have dramatic difference between complete and partial distribution. For magnesium lines, it is less dramatic. In fact, it appears only in the wings. So here you see the similar profiles as before. But for example, here, for higher pressure, you get this is complete redistribution wing, and this is partial redistribution wing. So in the wings, you see significant difference, but not in the line core, which is dependent on the Doppler broadening, on the width of the core. And in fact, this region is, let's say, rather noisy on the limb if we observe. So it's rather difficult to see this. So this is not so critical. Then the magnesium lines, in the same way as in the chromosphere, they are important coolants of the plasma, together with hydrogen, calcium, and other species. We did some calculations. Again, it is in that paper. I don't have time to go to details. But when we added magnesium to radiation losses, computed consistently, to other losses, hydrogen, calcium, we were able to compute radiation equilibrium temperatures of the prominence structures. And it is very interesting to see the values, whether the prominence can be in radiation equilibrium or whether it needs some extra heating. Actually, this kind of work for hydrogen was done 40 years ago here in Boulder by Dimitri Mihalas and Bob Milky. There is a famous seminal paper on such problem. Okay, then another paper which deals with observations and interpretation of observations is this one, where we considered one very interesting aspect. We observed magnesium 2 lines, but also we got observations of H-alpha lines simultaneous, and it appeared that H-alpha is very strong constraint for the modeling of magnesium lines. I will show you. The prominence was observed here. It was sort of quiescent prominence, but with a lot of dynamics and also some threads with larger velocities. So this is less dynamic part, and these threads contain a lot of flows with velocities up to 80 kilometers per second. Here you see the spectrum. Actually, observations have been analyzed and published by Brigitte Schmieder et al. 2014. Here you see magnesium 2 line. This is this more dynamic structure. It looks very broad. It might look like broadened by turbulence. The previous speaker mentioned something like 40 kilometers per second turbulent broadening, which is very high, of course. But I will show you the profiles. This seems to be combination of several structures along the line of sight, visible and shifted, Doppler shifted, so they produce some global broad profile. And this is narrow profile in more quiet sun. Here you see carbon-2, for example, carbon-2, silicon-4, which can give us independent constraint or diagnostics of hotter parts of the prominence, so-called prominence corona transition region. Okay, I don't have much time, I see. It's okay, so I will be very short. Here you see very narrow profiles. These profiles look broad, but as I said, they are probably composed of several Doppler shifted components. And so maybe we were able to fit these narrow profiles very nicely with our modeling, including some transition region between cool part and the corona. But as I said, the strong constraint was H-alpha line. Without H-alpha line, we could find other models which were not, of course, realistic. This is very important. I will skip this. And then I want to mention the last interesting topic, which is called Doppler dimming effect. Because if you have flows, large flows, we already computed this effect. The absorption profile, absorption coefficient is Doppler shifted with respect to the incident radiation, and you may receive either more or less incident radiation, which is then scattered. So if you have velocities here, radial, yes, in vertical direction, and moving plasma, so the magnesium integrated intensity with respect to the static case, which is this one, static case, you get first some brightening here, which is caused because your absorption profile moves up along the incident radiation peak up to here. And then it goes down because your radiation, incident radiation, is received from this part and finally somewhere here. So this is very dramatic, important. I think it was used also in other studies. The next speakers will speak about that also. Okay, so I will skip this. This maybe not. Okay, sorry, I have several slides. I only want to say that if you want some tutorial or the non-LTE modeling of prominences, you can go to this book, which was just published by Springer. It's a new book which was edited by Jean-Claude Vial and Oliver Engwald from Oslo. And it contains a lot of chapters by different people on prominences, and one of them is also about non-LTE modeling. Okay, thank you.
Thank you. There are questions? Yeah, Tiago?
Have you looked into the time-dependent ionization of magnesium?
In prominences?
Yes.
No, not yet, not yet. No, we did some modeling of time-dependent ionization for flares, but of hydrogen, yes, in our RH radiation hydrodynamic code, but not for magnesium, which would be similar technology. But in prominences, it can be interesting because, as you have seen on the first movie, it's highly dynamic. You know, these fine structures, they are lifetimes, it's well known since 80s from observations from SAC-peak, from movies, H-alpha movies. The lifetimes are of the order of several minutes. So if you have low density medium like prominences, then non-equilibrium ionization can be important, yes. Not only for magnesium, for calcium, hydrogen. Yeah.
Jotun, question?
When I look at the prominence, most of prominence has a single peak, but most of prominence in off-rim region has a single peak, single Gaussian-like structure profile. But some of them have a central reversal. But some of them have maybe superposition along the line of sight. And so
this is what I have shown.
Do you have any idea to distinguish the opacity effect and superpositions from the observational data? For example, using a ratio of the K and H ratio. Something like that.
It's a good question. Of course, we were thinking about that. But if you have just reversal, the width of the peak will not be so high.
Mm-hmm.
So
Yes.
you can look at the width, yes. And if the width is very high, then it is probably superposition of Doppler shifted
Yeah,
components.
because I don't want to use forward modeling.
I can show you later.
Okay, thank you.
Leaks.
Okay, let's thank the speaker again. And the next speaker is Peter Levens. I hope I pronounced that right.
That's right, yep.
And he's going to talk about prominence, plasma, and magnetic field structure using Iris, Hinode, and Themis data.
Yes, so thank you for those of you who don't know me. I am Peter Levens. I'm a PhD student at the University of Glasgow in Scotland. And I'm presenting some data here that I've been doing with Brigitte Schmieder, Nick Labrosse, and Arturo Lopez Arist on prominence, plasma, and magnetic field structure. So we ran a coordinated observation last year with a number of space-based and ground-based observatories. First and foremost, IRIS, obviously the reason that I'm here. IRIS we have slit jaw images, some lovely spectra from IRIS, but we also have Hinode, SOT. We have calcium-2 images from the campaign. And importantly, we have Themis. Now, Themis is a spectropolarimeter, and it can give us a measure of the magnetic field strength and orientation, which is important for prominences. So the observations themselves, for a bit of context, a bit of background, I'm going to be focusing on the 15th of July dataset, in which these AIA movies show we see these two tornado-like columns, which are the prominence legs. We see them in AIA coronal filters, 171 and 193 here, and almost make it out in 304, but 304 seems to show us more of the sort of the helium-2 cool prominence structure. So we label these T1 in the north and T2 in the south, just for easy reference. And moving on to look at the IRIS data. IRIS ran for 3 hours on the 15th. We have slit jaws and magnesium-2, like is shown here, also carbon-2. And we have spectra in magnesium-2 K and H, as well as silicon-4 and carbon-2. Now, the main thing I would like to point out with the movie here is that we really see quite nicely horizontal structure in the prominence. We also see some sort of motion in sort of loop-like structure in the front. The horizontal structure is quite important. We'll come back to that later when we're looking at the magnetic fields. So a bit further into the spectra, this is comparing magnesium-2, silicon-4, and carbon-2 for one slit. Now, the signal to noise that we have, the exposure is quite short, so the signal to noise is quite low for silicon and carbon. So we've had some of these data. But when we do that, these two bright prominence legs show up in silicon-4. And these are co-spatial with T1 and T2 that we identified earlier. The other thing that I'll just point out here is that carbon-2 matches pretty well with magnesium along the slit. So moving on into further detail into the spectra. the iris raster was a 16-step coarse raster with 2 arcseconds between each slit. Nearest the limb here on the left-hand side, and over on the right is the top of the prominence. You can see there. These are some spicules down here. This is entirely off the limb, so this is all prominence. Zooming in a little bit so you can see the spectrum more clearly, we can see that there's quite a complicated mix of reversed and non-reversed profiles. Now what we can do with these is identify our 2 prominence legs, T1 and T2. And what we notice is that the regions where the most reversal happens seems to be pretty much aligned with where these 2 columns are. Now what I'm going to show in the next slide is some cuts through 3 of these slits, sort of to give you an idea of what the profiles look like and how they evolve over time. And this is that. So at the top we've got T1, bottom we've got T2, slit 1, the middle slit, and the final slit. And what we notice is that generally T1 has a greater central reversal, especially here, compared to T2. But T2 has reversal nonetheless, even though it's less, and sometimes non-reversed. But by and large, we have mostly centrally reversed profiles. So there's a lot that we can do with this. But before I go into more detail about the spectrum, I would like to take you through our coordinated observation. So this image in the background is AIA 171 once again. The blue here sort of outlines roughly where the 2 tornado-like columns are. And overlaid on this we have the red box, which is the SOT and iris slit jaw field of view, which are shown on the right here. The pink is the iris rastering region, like I said, entirely off the limb. And the white and yellow boxes show the regions of the 2 Themis runs from this day. So Themis, it runs parallel to the limb, and we can get the magnetic field from that. So going back to the AIA images, we can sort of roughly mark out where the corners of these 2 structures are, which are marked here in blue crosses. And then we can overlay that on both the SOT and calcium and magnesium 2 images from iris. Now what we see is that the region outlined in the SOT calcium 2 by these blue crosses, we can see the prominence legs sort of showing up pretty brightly with sort of a bit less emission in the middle. But the same is not true in the iris magnesium 2. Now as Petter said in the previous talk, the optical thickness of magnesium 2 is greater than that of calcium. So what we're seeing in magnesium 2 is really the front of the emission region, whereas in calcium 2 we're seeing a bit deeper into the structure. We're integrating along a little bit more of the line of sight. So this is all interesting, but the other thing that we noted earlier is that where we see these, where we have these dark columns in AIA, we also have the central reversal in the iris spectra, the magnesium 2 spectra. So we're starting to get a pretty full picture of a pretty good observation already. But more to this, we have Themis. Now, as I said before, Themis is a spectropolarimeter. So it measures the 4 Stokes parameters, and we can extrapolate from them the magnetic field strength and orientation. We use the neutral helium D3 line for this, and the top panel here shows the intensity map, and where we see brightenings, the inverse color table here. Where we see brightenings in this, we see are sort of co-aligned with the dark structures in AIA. The second panel here shows the magnetic field strength. Now we see the strongest field in these 2 prominence legs of up to 50 Gauss, and this again is co-spatial with where we see the reversal in iris. So we can start to think about sort of magnetic pressures and that sort of thing with this data. The other thing I would like to point out here is this panel, which is the inclination of the field. Now you see it's pretty much orange, and that means that it's 90 degrees, which is horizontal, and horizontal in this case is parallel to the limb. So we have pretty much horizontal magnetic fields everywhere. The same is true in the other Themis run, which I've not shown here because of time constraints. So this is really nice. We've got a good coordinated observation. So going back to the iris spectra, we wanted, in this case, we wanted a sort of quick first guess at some of the line parameters, such as the velocity. So we fitted single Gaussians to the magnesium 2K spectra, and this is the result of that. I've indicated again T1 and T2 on the right-hand side here. Now, previous authors have shown apparent rotational motion in these prominence legs using other instruments and spectral lines. Some of these papers along here have shown that. But we see absolutely no evidence of that in magnesium 2. So what do we see? Well, we see line of sight velocities on the order of 5 or 10 kilometers per second. And we also it seems to match the sort of horizontal sort of structure that we had before. So that's interesting, but we wanted to go a little bit, look at the profiles in a little bit more detail so that we can compare these to the theoretical models, the theoretical radiative transfer models. So this table at the top is some of our line parameters. I peak and I naught are the peak intensity and the central reversal intensity for the K line. And IK and IH, we did some analysis of the moments of the distribution of the function, of the profile, sorry. So that's where we got the IK and IH values. So comparing this to the Heinzel model, we can, for a sort of fairly good, reasonable values for the prominence, thickness, and temperature, 1,000 kilometers and 6,000 Kelvin, we can constrain the gas pressure as well as the optical thickness for these lines. Now, comparing the peak value, the peak ratio to the central reversal ratio, we can see where these two columns lie, and that gives us this sort of region. So we see gas pressures of somewhere between 0.1 and 0.5 dyne per centimeter squared, and optical thicknesses of 140 to 820, which is really huge considering, like as Peter said, for a similar gas pressure, we'd expect H alpha to be somewhere in the region of 1. The optical thickness of H alpha to be somewhere in the region of 1. Also consistent is the K over H intensity ratio. So that's all of the slides that I have. Put up a quick summary. We've got this lovely coordinated observation where we see reversal in iris, brightenings in SOT, dark structure in AIA coronal filters, bright in Themis, helium-1, and a strong magnetic field. We have no evidence of rotation in the magnesium 2 lines, and we've compared this with radiative transfer models. The 1D case, which I showed, but also it compares pretty well with the two-dimensional case of PAL2. We have gas pressures of 0.1 to 0.5 dyne, high optical thickness, and with the gas pressure and the magnetic pressure that we'll be able to get from Themis, we can start to think about MHD models. So all in all, it's looking pretty good. So that's all. Thanks.
Thank you. Question, Phil?
Yeah, that was very.
That was very nice. The only question I had was, what is the relationship between the magnetic field vector and the structures that you see there? So you did say that I think it was the inclination that was horizontal relative, so that it was not inclined to the line of sight. In this, out of the board, the magnetic field is in that direction.
So
what about the azimuth? Is that compatible with what? I don't know.
Well, the azimuth we see is pretty much somewhere, it seems to be slightly tilted into the board. So, I mean, the inclination is sort of in the plane of the board, where the...
Oh, so this is not what spectropolarimetry people called inclination. Inclination is the angle of the magnetic field relative to the line of sight.
Oh, that's the azimuth, the line of sight azimuth, I think.
Okay, so could you please clarify what the structure is that you're seeing? If you said most simply, where is the magnetic field, what would it look like?
So, in the plane of the sky, it would be sort of horizontal like this, okay? Yeah. But the azimuth sort of suggests that we have maybe slightly slightly sort of tilted away from us.
And do you see, the next question is, do you see plasma motion only along those directions, or is it sort of all over the place in this prominence?
Where is it? So in the line of sight velocities, we see sort of structure moving in these sort of threads, horizontal threads, both backwards and forwards. And also we see the plasma moving along in the plane of the sky as well, from the intensity maps from like the slit jaw, for example. We see sort of apparent motion in that direction as well.
But the tornadoes are vertical-like structures.
Mm-hmm. Yeah.
So that's different. Is the magnetic field there horizontal?
Well, it doesn't. I mean, it doesn't look like it from the TEMIS.
Okay.
So this is maybe pointing more towards the sort of dip models, with the dips, and then so. But there's more to investigate with this. The problem with looking at the magnesium-2 line of sight velocities and sort of intensity maps is, of course, the optical thickness. So we're just really seeing the front of the emitting region, whereas these two structures appear to be sort of further into the prominence, so sort of more central. So we're not really seeing those here.
Okay, while Jean-Claude, you want to set up? Okay. Are there any other questions while we're setting up? If that's not the case, let's thank Peter again.
Should be okay. And now this is F8 or something, yes.
And the next speaker is Jean-Claude Vial, who's going to talk about quiescent prominence threads observed with iris and a comparison with non-LTE models.
Okay, thank you. I think Petr already showed some spectra, iris spectra of prominences in the magnesium HNK doublet. And in order to disappoint you have seen very nice spectra at the South Pole. In order to disappoint you, I will show you some results concerning very small threads, which we think are important actually in the determination of the physical conditions in prominences. This is related to the issue of the fine structure in prominences. We think that it has been clear that it is limited by the spatial resolution of the present instrumentation. Evidence comes from the very old H-alpha SAC-peak and others, recent Lyman alpha from Volt, H-alpha calcium-2 from SST and ST, SOT, and so on, which show that the structuring, the scales could be less than 0.15 arc-second. There is also some evidence from spectroscopy, including in UV. You can have a look at the paper by Engvold with a filling factor of less than 0.02. Other people address the issue in another way, that is trying to derive the number of threads along the line of sight, from 20 up to 100, for instance. So it's a very large number. And finally, some work has been done on the modeling with a bunch of threads. This has been already mentioned by Petr. You have these threads are transformed into layers, and you add up the proper number of layers, and you can also add velocities of these structures. So this is, we think, an important issue. And I think we used the exceptional resolution of iris in order to understand that. The spectrum that was obtained, that was shown by Petr, was obtained here. So we like doing difficult things. So actually, we worked on this structure, on these small threads here. This is a carbon-2 channel in log scale. It was obtained pretty early in the mission, so there are some problems related to the calibration and so on. I will address that. The point is that there were, at this time, no simultaneous magnesium-2 spectra. So what to do? We look after spectra, magnesium-2. This was obtained 20 seconds before. And perhaps people who have a good eyes, good sight can see something here, but this is in linear scale, so we have to move to log scale, and then we have some pieces of material here. And this is what I will discuss today. You of course, K and H, you have everything you need to know what happens. We also had some, we also looked at some H-alpha observations, BBSO, TIDE, rather simultaneous, within 10 seconds maybe, or 20 seconds, less than that. And this is we added the field of view of the slit jaw camera of IRIS, and our observations do not take place here, which is so easy to, but they took place there in order to trying to cut elementary threads. The same, we happened to have a stereo EUVI images, but they were at A was here and B was here, and essentially they showed edge on and head on. But the point is that we couldn't properly analyze these, get the proper geometry, because one of these images was taken maybe more than 1 hour before, so it's a bit difficult, tricky too. Finally, AIA. So this is helium-2, of course, and this is after some work. We put, this is the location of our slit. So we will focus on these two structures only. First of all, I want to discuss the issue of calibrations. It was already addressed by other colleagues, Thiago and others. At this time, we used our own technique, which is the one that is used by IRIS people. So as far as wavelength is concerned, we use the manganese line, absorption line as a reference. And as for photometric calibration, we paid much attention to that because we feel that it is important in order to compare with modeling, the results of modeling. So we use two methods, the pre-launch method and what we call the KP method, that relies upon the fact that we assume that the quiet sun right now in 2013, at the time of strong activity, was the same as at the time of Colin Parkinson, which was a minimum. So you see the difference between the two. This is K profile, of course, and this is one method and the other method, with a difference of about 30%. So, well, it should be, but this difference is within, I would say, the errors. And moreover, as you will see, we use the other values provided by Jean-Pierre Wulzer, and I encourage you to see his poster 41. So, after having solved that, we return to the issue of our threads. So you see, this is we turn the slit jaw camera image, and we make a cut along the slit. This is in red the K intensity, in green the H intensity, and our poor threads are here, you see? And this is with an intensity which is less than 10% of the disk intensity. By the way, this rectangular here, this is the place where we selected our quiet sun values at cosine theta equals 0.23 in accordance to Colin Parkinson. So let us zoom on that region, and this is the signal. Here I return to the raw signal in order that you have an idea of the statistics. Red is K, green is H, and we selected these two set of threads here. I remind you that this is in 1/6 arc seconds. So the structure is about overall about 8 arc seconds, no more, at least 8. So let us see a few results of that. First of all, as has been mentioned, this is interesting to look at the flows in these structures, especially since we have a very fine resolution. And this is a stack profiles in region A, K, and H. I don't go into details here, just but you can see this kind of wave here. This is in kilometers per second. Sorry, I didn't put the scale. And velocities are less than 8 or 9 kilometers per second. Are there flows? Are there oscillations? We don't know. Now, we built some average or mean profiles with again, these two techniques, but we will not discuss that further. In region A, K, H. In region B, K, H. With, of course, the scales are different here and the intensity are low. First of all, as was already mentioned, these profiles are unreversed, basically. Let us see the properties of these profiles in region A and region B. This is taken from the table, so I didn't want to, but this corresponds to the three types of calibration. This is pre-launch, this is Colm-Parkinson's, this is the Wulzer or Solstice method. Forget about that. Let us focus on the physical quantities, IK, IH, the ratio, which is around 1.41 to 1.5 something, which is so unreversed profiles, K over H about 1.5 is a ratio. And from the full width at maximum, we derive the non-thermal velocities of about 10 to 15 kilometers per second, which is important, provided we have a low temperature. Now we compare with the modeling that was discussed by Petre, 1D modeling. When you have unreversed profiles, low K and H intensity, basically you have to, in principle, you have to have, without any strong velocity field, the only model that fit are low pressure and or low temperature and or low thickness. Something like 200 kilometers, 6,000 degrees, very low pressure, 0.01 Dn per square centimeter. You can wonder, this is the effective thickness. Of course, this means that if this is the right model, this means that you have a very small filling factor, since our observed structure is about how did I say, 8 by 3,000 kilometers, something like that. But the point is that when we look at these models, the K and H values don't match the model values simultaneously for a given model. In other words, this means that the K over H value is larger than the observed one, within, of course, the precision of that. So we also try to use complementary observations. H alpha was very low, but as was mentioned by Petre, from these values we can derive some emission measure, and then derive some density, very low density, which is not a surprise, but we also have to be careful because these are rather narrow band passes. And so maybe the velocities can shift the profiles out of the bandpass. The slit jaw, we didn't use the slit jaw data because it was so faint. We used the data of helium-2 just to have an idea of what was happening. We built this ratio, and we found the ratio between the prominence intensity to the disk intensity, which is about 0.4. Which is about the dilution factor. So that means that helium-2 just reflects the incident radiation. This is in region A. In region B, we have this value, and we don't know where we have to interpret it. Okay? And now, so to conclude here, the key issue is the low value of the low value of the ratio K to H, which has been already observed a long time ago, but more recently now by Schmieder with Aries. And I will just finish with some discussion. About this ratio, we have different possibilities to interpret that. It was already mentioned by Petre. Radial velocity, which led to Doppler dimming. It requires large velocities, but we have to perhaps do some new computations. The multi-thread structure that I was mentioned by Petre goes in the right side, in the right way, and increases K to H. And now we are thinking about line-of-sight projections of strong flows in low-pressure structures, which preliminary computations show that we can reach a value of 1.45. What about the plans? Of course, the analysis of well-separated threads, again, perhaps in the frame of campaigns already led and so on. Our only concern is that as soon as you want to observe tiny threads, elementary threads, you get a low signal. That's life, and that's my conclusion.
Thank you. Questions for Jean-Claude? Okay, now I have a question. Have you tried applying this on a statistical basis on a variety of data sets?
No, we should. Yes, that's right.
Because this data also, I noticed it was the day after first light, I think.
Yes.
I'm not sure how good the focus was.
Yes, as I said, we like difficulty. But this data was, Alan Title pointed out attention to this data, and we work on that. But for sure, we have to work on not new observations, but to just analyzing and build some statistical. The data, you have data, perfect, very good data, no doubt about that. But,
so I guess I'm not a big expert in prominence physics, but I'm guessing that what you're doing is trying to constrain theoretical models.
Yes, yes. And by the way, we found perhaps another path, another solution, a set of solutions, when you include the strong velocity fields, which led to strong Doppler dimming, with a solution with higher temperature than the one which I mentioned. But this, I think we have to, the best thing to do is to build this, first of all, to build a statistical study of observational, and then to play with the models.
How easy is it to run this on a whole bunch of data sets? I mean, is there a lot of manual work involved? Or?
Oh, it was manual work, yes, made by, yes, very manual. I'm sorry, but I would like to have a tool like proposed by Bernard Fleck, but no. No, it was manual essentially because at this time we had not the fine routines that you have now.
But is it manual in terms of co-alignment, like Bernard said, or was it? I was asking actually about the theoretical modeling.
Manual, of course. Yes,
yes, but in terms of
we use a 28,
modeling.
32 angstrom line, stuff like that.
But what about the theoretical modeling? Is that pretty automated?
It relies on table 2 of the paper by Enza.
I see.
Essentially.
Okay.
More or less.
You're walking away with the microphone.
Okay.
Let's thank Jean-Claude again.
No.
And our next speaker is Wei Lu. His title isn't fully visible. I think you need to reset the... He's going to talk about prominences, but I can't read his full title, even though I'm a co-author on this, apparently. A novel hybrid prominence corona.
Hybrid prominence corona ring complex in the neighborhood of null points.
Okay.
Let's see, display.
So you got 10 minutes, right?
10 minutes?
Yeah, just a reminder, it seems that everybody's surprised when I remind them it's a 10-minute plus 5-minute discussion, 10-minute talk plus 5-minute discussion. So that is the norm. We want to promote discussion. So. Yeah,
okay.
You have to confirm, otherwise it's hiding.
This one. Yeah. All right.
Yeah. And I got the clock running there.
Okay. All right. Good morning, everyone. So I'm going to talk about a potentially novel type of structure we call them hybrid prominence corona ring complex. So here's my outline. I'm going to go through a very brief introduction about why prominences and corona ring are important and what are the similarities and differences. And I will follow up with some new observations by Iris and discuss their implications and summarize. So why are they important? There's a newly recognized concept called Chromospheric chronomass cycle. Namely, hot stuff would go up from the chromosphere to fill the corona, and there's a cooling process that returns those cooled mass in the forms of prominence and the coronal ring back to the chromosphere. And the prominences and the coronal ring are two most important forms of this return flow. And what we usually see as prominences are those like filamentary downflow threads and a very meandering path. And if you look at coronal ring, it's going to be quite different. So here's what Iris saw in a coronal ring event. And what you see is very well-defined trajectories along active region loops and in quiescent states and also during flares. The contrast between these two phenomena is the path for coronal ring is well-defined, curved path, but for prominences, these meandering threads are very irregular shapes. So here's some new observation we got from Iris and AIA SDO about some new structure called prominence coronal ring complex that may shed light about why the difference between these two phenomena. So here's what the geometry is. So basically, there's several active regions, and you have something like a fan shape above some arcade loops. And Iris was sitting right here, watching this area. And let's move on to next slide to see the movies from AIA. What you see here is yellow is 171, about 1 million Kelvin. Red is 304 helium. Very cool material. What you see here is right at this edge between this fan-like structure and those underlying arcade loops, there's a prominence thread-like structure forming right there. And as this material descends further down, they end up on the loops and it turns into coronal ring. So that's why we call them prominence coronal ring complex, because they have different morphological characters and different geometry in terms of the magnetic field structure. And here's what we see from 171 alone. What you can see better, the loops underlying them, and there's seemingly open field, whatever. And but the boundary between these two regions are very pretty sharp, and that's where this prominence material is formed. And move on to look at time slice, look at different channels from AIA, from all the way about 2 million Kelvin down to like 304, about 80,000 Kelvin material. And what you can see here is there's a brightening delayed in time lasting several hours. And this is indication of cooling. So this cooling is responsible for the formation of this cool material as a prominence and eventually coronal ring. And let's turn our attention to what Iris see. So here's an Iris raster scans, slit jaw on 1400 silicon, and this is the spectrum from magnesium 2 K line. So what you see here is the top portion is very irregular flows, like sloshy back and forth, and sometimes tumbling flows. But the lower portion is very regular, well-defined path coronal ring. So another thing you noticed here is the top portion has broader line width, and the lower portion has narrower line width. And if we take a look at some snapshots, so the character of broad line width at the top and narrow line width near the lower portion is pretty clear. And if we do some spectrum fits, Patrick Antolin did this automatic spectral fits for about 30,000 automatic fits. Basically, what we show here is the Doppler velocity, histogram, and line width, and the non-thermal velocity. Another thing interesting here is plot those fits as a function of height. So we basically will see a very broad distribution versus height, but the clear trend is if you look at the non-thermal velocity, there's very broad non-thermal velocity at the top portion, but lower velocity in the lower portion of it, so where the coronal ring is. So looking at the Doppler velocity, as clear, is they have lower velocity at the top, higher velocity at lower portion because the coronal ring is accelerating as they travel. And if you take a closer look at those average values for Doppler velocity, line width, and non-thermal velocity as a function of height, what you see here is, if we focus on the this portion where the transition from the prominent threads to coronal ring is happening, you see a very clear decrease of line width and non-thermal velocity as they descend further down to lower heights. And if we move further down, when they turn into coronal ring entirely, not much of change in the line width, but of course there's an increase of velocity as they descend. So let's move on to next slide to look at the geometry on a global scale. So here's a movie from AIA 171 overlaid on HMI magnetograms. I'm going to play the movie. So what you see here is the west is up, north is this way. So basically you see several active regions evolving over time, but when they turned about close to the limb, this region of this fan-like structure formed. That's where the coronal ring and the prominence material is forming. And if we do some triangulation with AIA and the stereo to look at the 304 co-material, and we can pinpoint where those material is formed in absolute location. And Dr. Shidong Sang did this triangulation and found the location, and here's where this lips located between several active regions in the and obviously these active regions form some sort of quadrupole structures, and in the neighborhood there are several null points. And if we take a look at from the limb view, rotated, and you see these regions are pretty close, but of course it's not perfect because the magnetograms were taken about 3 days ahead of the occurrence of this coronal ring on the limb. That's the best we can do. And the difference between their location could be because of the evolution of the magnetic structure over days. But this is pretty encouraging because we found clues why this is happening here. And the several null points are pretty close to the location. And there's some close-up of null points. Basically, you have some sort of very complex structures where this coronal ring might be happening. So why null points are important for prominence or coronal ring? One important feature is the so-called condensation process, where non-thermal or thermal non-equilibrium. Basically, that's because of the loss of the radiative loss function of the coronal material is a decreasing function of temperature from about 10 to the 5 to 10 to the 7. So in this region, if you have a temperature perturbation, have some sort of cooling, it will go into a runaway cooling instability. And another important ingredient here is the magnetic field, because in the million degree corona, conduction is so powerful, you have to have magnetic field to make this thermal conduction anisotropy, and so that can perform like an insulator when you, for example, when you have a null points, and heat flux cannot get into this O-type null points. So that can be in favor of cooling condensation. And another several points about null points is when you have null points, probably have the null points can deform into current sheets. And in the current sheet, you have structures like chaotic or entangled field. And in these locations, entangled field can also suppress thermal conduction and in favor of cooling condensation. And also they can contribute to those meandering flows for the prominence material. And another thought came into my mind was this, when you have a current sheet, you probably have a weak field in the neighborhood. And similar to the situation in those so-called superarcade downflows in flares, you have some sort of fluid-like flow rather than a low beta plasma situation. So that's another possibility. And there are more possibilities, like including this interplay between condensation, cooling condensation, and it can also deform the magnetic field, and eventually, sometimes it can cause reconnection and produce null points, or the so-called null O-type structure. And this list goes on, but the key point is null points can be very important for condensation, and there's flow characters in the prominence material. So just a few more examples. So here's another example caught by Iris. There's a very clear fine spine geometry where the corner ring material is formed right here at the null point. And we can model this geometry with extrapolation with a clear fine spine geometry where the corner ring is formed. And more examples. So what you see here is the cusp structure, very long line loops. But watch closely, this red cool material is formed right there at those cusps. So those are probably locations of null points, X-type or L-type or whatever. And the situation is there are preferential locations for corner ring condensation. And there is more extreme examples. You see tumbling flows in 171 cool material, and then suddenly will turn into red material, and the yellow cloud is gone. So, and in the lower portion of it, you see clear indication of corner ring structure, like later on. Just wait. This is very well-defined path, but the top portion where the material is formed is very chaotic. So in summary, so we propose some sort of new paradigm of prominence plus corner ring complex, and hopefully can give us some new clues about the distinction between these two phenomena, but they are also very closely connected because they both serve as the return flow of the chromosphere coronal mass cycle, and they share very many similarities, and the distinction between their morphology could be because of this magnetic geometry. For corner ring, they end up on the loops of high magnetic field strength and probably in low beta saturation, so the material can be guided by the field, so they have well-defined path. For prominence material, they are likely in the neighborhood of null points or maybe current sheets, so that provides some sort of environment for their, first of all, cooling condensation and also their flow pattern. Thank you.
Thank you. Any questions? Okay, I have a question. Some of the examples you showed at the end there looked like just coronal rain. What was the prominence aspect of some of the AA movies you showed at the end?
Yeah, somehow. The first one with the big dip, that's similarly like the coronal ring, but the point is they happen at the dip, so that's the connection to null points. So in one sense, the distinction between these two phenomena may not be that clear because they share similarities, but the common thing is they all form from condensation or from a cooling process, and the null points could be very crucial for their formation.
Okay, thank you. Marcus?
And how do you explain that the speed of the downfall in the rain is usually third or less than free-fall speed? How do you explain this scenario?
So that's more applies to coronal ring because you're not falling in a vacuum. So there are scenarios like wave breaking where you probably have thermal pressure breaking the falling material because you are still, the blobs, cooling blobs are still falling along loops filled with plasma, not empty loops. So there are definitely some pressure or other ways to slow them down.
Okay, any other questions? If that's not the case, let's thank Wei and all the other speakers again. And we have a poster break. We have 2 e-posters in the room over there, and we reconvene at 11:30.
Sorry. Okay, I'm going to talk about penumbral microjet, again, observed by IRIS. So I can skip most of the introduction, but we did a lot of study about the penumbral microjet, including the jet light brightenings along this magnetic field line. And we also confirmed that this jet light brightening happened along the vertical magnetic fields by the comparison with the Hinode spectral parameter data. And also we have the observation of the photospheric feature associated with the penumbral microjets using the, again, Hinode spectral parameter and find some downflow patches associated with chromospheric brightening. So this is why we speculate that the magnetic reconnection happens somewhere above upper photosphere or lower chromosphere. It makes upward jet seen in the chromospheric lines, and in the photosphere we can see downflow associated with brightening. So this is our current interpretation. But actually, if the reconnection happens in the photosphere or lower chromosphere, it's almost impossible to generate a fast jet, because if the reconnection happens in the lower chromosphere, plasma beta is usually almost 1. So if energy release happens in the lower chromosphere, it just generates a sound speed jet, or alphonic velocity is just 100 kilometers per second. So it's hard to generate a very fast speed if reconnection happens in the lower chromosphere. So some people think that the waves are important to drive the high-speed jet in the relatively upper chromosphere. So energy should be carried from the lower atmosphere to the upper atmosphere by using some waves. Is one interpretation to drive such high-speed jets. And also we made a study using the IBIS at DST to find the spectrum signature of the penumbral microjet. So we found the L1 bomb-like spectrum profiles in the calcium-2 lines, and we found that some cases we found the blue wings are enhanced, suggesting that some upward flows, but the velocity is 10 kilometers per second. So actually, this velocity is much slower than the apparent motion of the jet. So using the IRIS, we want to study how that these penumbral microjets influence the upper chromosphere or even higher in transition region corona. And also, we should study how that velocity evolves along the penumbral microjet to study how that very rapid motion is driven. Okay, so we did the study observation using the Hinode and IRIS, so-called HOP250. The unique feature of this HOP250 is that we use a very high cadence calcium filtergram observation. 1.6 second cadence currently is the highest cadence that can be achieved with Hinode. And also we got the IRIS data, Sweetgel, and also we compared the AIA. And also we took the sparse dynamics mode with the Hinode spectral parameter to study the temporal evolution of the magnetic fields in the photosphere. But in this talk, I mainly focus on the comparison with the Hinode calcium filtergram and the IRIS Sweetgel and IRIS spectrum. Okay, this is some example of the penumbral microjets. And yeah, we can clearly see the penumbral microjet after the Fourier filtered calcium filtergram. And then we found correspondence in the Sweetgel, maximum to Sweetgel. And we can see the bright dots associated with penumbral microjets in the silicon 4 line. Okay, so we can see the penumbral microjet in the calcium filtergram, and almost similar structure is seen in the magnesium 2 Sweetgel. And then in the silicon 4 Sweetgel, we can see the bright dots associated with the outer end of the penumbral microjet. In this case also, the elongated brightening is seen in the calcium 2 and the magnesium 2, but usually the magnesium 2 jets are longer than the calcium 2, and then we can see the bright dot in the silicon 4. And sometimes the silicon 4 brightening is elongated along the jet. In this case also, the calcium 2 and the longer jet is seen in the magnesium 2, then we can see the silicon 4 bright dot at the end of the at the outer edge of the penumbral microjet. So actually, this bright dot seen in the silicon 4 was already reported by Hui Qian last year, and he reported that sometimes that it has the sub-arcsecond bright dots, but sometimes it has elongated shape parallel to the filamental structure of the penumbra. And also, he reported that the lifetime is less than 1 minute, and it has some apparent motion, 10 to 40 kilometers per second. So in this study, we clearly found that this short-lived bright dot seen in the silicon 4 sweet jaw is a correspondence to corresponded to the outer end of the penumbral microjets. Okay, this shows the temporal evolution of the penumbral microjets using the time slice along the jet. So this is a clearest case when we can see the acceleration of the jet. This is a calcium 2 filtergram, and this is a filter, Fourier filter, a calcium 2 filtergram, and this is a sweet jaw magnesium 2 sweet jaw silicon 4. Then, because of the high cadence of the calcium filtergram observation, we can see the clear acceleration here along the jet. At the bottom, the velocity is slower than 100 km per second. Then it rapidly accelerates faster than 500 km per second, or in this case, it's almost 1,000 km per second in the chromospheric lines is seen. And in the sweet jaw, because of the cadence of the sweet jaw is 10 seconds, we cannot resolve the temporal evolution. But again, we can confirm that the silicon 4 brightening is associated at the end of the calcium penumbral microjet. This case also, we can see some acceleration. Near the foot point, the velocity is almost 100 km per second. Then it accelerated faster than 400 km per second along the jet. But actually, in most cases, we cannot clearly see the acceleration. We can just see the rapid propagation from the inner side to the outer side. But still, we can see the evolution, temporal evolution of the penumbral microjet, and the velocities, this case is faster than 400 km per second. Then we can see the association of the silicon 4 brightening at the outer end. Okay, this is an example of the spectrum of the associated with the penumbral microjet. Of course, it's because it very depends on the where the slit is located with respect to the penumbral microjet. But in this case, the filament is almost parallel along the penumbral microjet happens almost parallel along the slit. So we can see the temporal evolution of the spectrum at several locations along the penumbral microjets. And here we can see the magnesium to wing emission. And also we can see some blue wing enhancement here. But we cannot see any enhancement of silicon 4. But here we can see, still see the wing enhancement here, and then we can see the silicon 4 brightening here. And then wing enhancement is not so clear here, but we can clearly see the silicon 4 brightenings here. So again, we can confirm that the silicon 4 brightening is clearly associated with the penumbral microjet. But yeah, this is already reported by the previous speaker, and the velocity, there is some Doppler shift in the silicon 4 lines, but the velocity is 10 km per second or so, so actually much slower than that propagation speed. Actually, we tried to find a very fast Doppler shift associated with this kind of brightenings, but we haven't found such strong Doppler shift. So I think that that apparent motion seen in that calcium filtergram cannot be explained by the true mass motion, because such high speed, say, faster than 400 km per second or so, cannot be explained by true mass motion in the chromosphere. Okay, this is a summary of the Hinode iris observation of the penumbral microjets. So penumbral microjets are clearly identified the iris slit jaw data. And in the magnesium 2, the shape looks very similar, and the silicon 4 brightenings, bright dots are associated with outer edge of the penumbral microjets. And in this observation, by having the high cadence, 1.6 second cadence calcium filtergram, we can clearly identify the acceleration of the jets along, at the foot point, the velocity is slower than 100 km per second, but along the jet, the velocity is accelerated, and up to 400 to 1,000 km per second is observed in the upper chromosphere, in the upper part of the penumbral microjets. But most of the events, we cannot see clearly the acceleration, but still we can see resolve the temporal evolution of the jet, and the apparent velocity is faster than 400 km per second. And also, important thing is that we cannot see the deceleration For example, if we look at the spicules, we can see the upward motion, and also we can see the downward motion. But in this case, we can see only the upward motion. Okay, so this is a configuration like this. So the summary of the observation. Okay, and I want to show the. We made a more detailed study using the IBIS, calcium to infrared turbulent line. And yeah, this is a movie of the spectrum of the calcium to infrared turbulent line observed with IBIS. This is a wavelength versus position along the jet. And we can see the propagation of the jet along the propagation of the enhancement along the jet. And can you see the finally the near the outer side of the jet, we can see the core emission slightly. So it also suggests that some propagation happens at first we can see the enhancement at the outer wing, then after 5 seconds or 10 seconds we can see the core emission, so it reaches to the upper chromosphere. Okay, so let me summarize my talk. So we can clearly identify the counterparts of the penumbral microjets in the iris observation. But still, the question is what makes such very rapid acceleration and heating in the penumbral microjets? It's still not clear. So I speculate that the propagation of alpha waves is only the possibility to explain such very fast speeds. If the magnetic field is very strong and the density is low enough in the upper chromosphere, probably it's such high-speed motion may be explained. But still, we need a lot of study. And also, I don't explain in detail, but we can see some counterpart in the AIA 171 image also. So there should be some influence to even the corona. That's all. Thank you.
I know, but looking at a lot at those FUV spectra, I'm not sure there's enough signal to noise to see the real counterpart of these things that are so fast. Any questions? Oh, there's we.
So do you always see the iris bright dots in the higher parts of the penumbral jets? I mean, in our paper, we also found some iris bright dots located at the foot point of fast jet from early iris schedule observations.
Well, if we pick up only the how to say, clear example, clear event of the penumbral microjets, the silicon four brightenings are always, in most cases, associated with the outer side, I mean the upper part of the penumbral microjets. But some cases we cannot clearly see the counterpart of the penumbral microjets associated with, when we look at the silicon four brightenings, sometimes calcium brightenings are very faint and not so clear. But most cases, my impression is that the silicon four brightening is associated with the outer side, I mean upper part of the penumbral microjets.
Last one.
So the spectral morphology of your features resemble several features that Luke showed yesterday, the dynamic fibrils, where they have seen the acceleration of the plasma or some structure and then appearance of these dots in the silicon. But then according to you, you don't see the reverse motion. Is it because that there is too much of background and it's really interpret or see the reverse motion?
What do you mean, reverse motion? Is there?
If they're shock related, is that what you're talking about?
Yes.
I mean, are these things, I guess he's asking if these are shock related, why don't we see the decelerating phase? Does that mean they're not shock associated? That you don't see the deceleration?
Well, we cannot, as I showed, we cannot see the deceleration at all. We just propagate upward, then it makes a silicon four brightening. That's it. So, well, we need, I think, a much higher temporal resolution to resolve the temporal resolution, resolve the temporal evolution in the upper part, because the current 10-second temporal cadence is not enough to resolve how the jet propagates in the upper part.
But we can run that much faster.
Yeah, I want to try.
Too much in the spectra.
Yeah.
So you will see stuff in magnesium, but we could probably run this at 2 seconds.
Really?
Yeah.
Oh, really? Yeah.
So thank Yukio again. Thank you.
Thank you.
Excuse me while we play with a dongle.
I dingle as I dongle.
Picking you up. Here it goes. Our third presentation of the session comes from Dr. Philip Judge, someone who I've known for far too long. Is that appropriate?
Yeah.
Yeah. And he's going to give us a talk on UV spectra, bombs, and the solar atmosphere. So take it away, you get 15 minutes.
So I'm, as you said, Philip Judge, and I'm a recovering Englishman. I would like to talk to you today make some comments on spectroscopy of the solar atmosphere, especially in the Iris region, with special reference to a Peter et al. 2014 science paper on bombs and UV photons emerging from, quote, the photosphere, which I found particularly shocking since the path length of a photon in the photosphere is centimeters or something like this. So first of all, what are we talking about? These are unusual things, and those of you that have seen the sextet papers in science from the IRIS mission will recognize some of these. Basically, the box regions are places where brightness occurs, and they have spectra of these things. You can slit your images on the top left, magnetic field. There are bipolar regions associated with these things. And then as you get out into the more AIA-like arena, you see the notable absence of anything, especially in 304. Silicon-4 is not that different in temperature from 304, therefore they invoke something called absorption in the Lyman continuum to remove these things. Here's a movie of these things. So these are small and these are well documented. And I'm going to talk about the spectroscopy of these things here. I won't show you the quiet sun spectra because they don't look anything like this and they're very boring. You've seen plenty of them before. But basically, this is the most dynamic bomb they could find with the most extreme case. I'm going to look at that one. What you find is these are line profiles with Doppler shifts marked on the x-axis, including the lower transition region, corona, some irrelevant line in the chromosphere, and then magnesium-2. There is some similarity between these things. In particular, the magnesium and silicon, that seems to be a running theme with IRIS. You get a lot of similarity there, which is very interesting considering how different they are in temperature. The point that Hardy et al. Made was that they're missing oxygen 4 lines, and they claim that these are optically thin. That's incorrect. These are effectively thin. The reason it's incorrect is because the ratios of the cores are not 2 to 1. Quite a long way from that, so that's an error they made there. These are effectively thin. What that means is you can't actually interpret the data in terms of velocities anymore. They went ahead and took some calculations from Chianti, black box kind of work with, in which there are some major assumptions being made, and they come up with an electron density based on the absence of the oxygen 4 to silicon 4, and they came up with a density of 5 × 10⁻13, which is about the pressure, total pressure of the temperature minimum, the classical temperature minimum region that Gene Avery has worked on for many years, and Jeff Linsky and Tom Ayers and other people. This is the highest density case. Is it really formed out of photospheric plasma? I believe not. I think that's a very difficult thing to understand. One thing I think I want to draw attention to is that most of the solar atmosphere is relatively benign. Most of the work done with IRIS is concerned with very dynamical things. And nevertheless, what I've shown you here is some basic structure of the atmosphere of the sun is that it's stratified between -100 to, say, a couple of thousand kilometers. And no matter whether you have piles of spicules and other things, those originate from within this plasma. They are not the chromosphere itself. You have to go from photospheric pressure to coronal pressure through a set of stratified layers. And what I'm showing you here, just for those of you who don't believe me, is this is a PDF showing you the distribution from a randomly taken Bifrost calculation, Bifrost calculation, versus the stratification showing you the log of the pressure against height. This is not very often appreciated. The sun is a the gravity is so strong in the lower atmosphere that the dynamics can't possibly do very much in those regions there. And we don't see a lot of line profiles that are very broad just in the lower chromosphere lines. So it's basically hydrostatic. If you have that kind of stratification, you'll see that at 500, below about 600 kilometers above the tau equals 1 in the photosphere, you basically run into an optical brick wall. You get 10 to the minus something here of a probability of escape from a continuum of that wavelength. This is a scattering continuum. You say, yes, it can emit at other frequencies, but it doesn't come back inside the line itself. Basically, any monochromatic line that gets absorbed by that continuum gets re-radiated at some other wavelength in the silicon continuum, and is not then counted as a line emission. So that basically is an absorption. So that tells you by how much the thing is attenuated. How on earth do you get 140 nanometer photons escape from regions with pressures above 550? Peter et al. Claimed it was below 450. That's demonstrably wrong, I'll show you in a minute. But this is a basic problem here about spectroscopy, which I think needs to be emphasized. The densities, first of all, I'll skip over this because it's quick. We know that silicon 4 versus oxygen 4 is a dangerous thing to do. Two different ions, very different temperatures, factors 2 or 3. If you did that in the photosphere, you'd be in real serious trouble, but everybody seems happy to do it in the transition region. So basically, first of all, though, we have different abundances, and if one has flares, one can easily have a situation of a dynamically active atmosphere, which this is a part of, in which you get separation of separation of elements by first ionization potential. Bottom line is silicon might be stronger only because of the abundances. The second case is that it's known for decades that the silicon lithium-like ions, sodium-like ions, are all much stronger than they should be. So there's an offset somewhere in the physics of our understanding of this, even in something benign like the quiet sun, which hasn't been taken care of, about a factor of 2 or 3 again. The biggest problem with their work, though, is the assumptions they make have to determine a solution. There is no unique solution unless they specify what they're going to get out of this thing. And the reason for that is, of course, that you have to make some explicit assumptions, but the implicit ones are really dangerous. The sources are of equal strength. They didn't say how much emission there is at the temperature of silicon 4 versus oxygen 4. I had to solve for that myself and came up with a number of 1. So depending on whether the emission measure is got this direction or that direction, and this is transition region plasma in which you could well have a cool loop solution. There could be 100 times the amount of cool loop material at 10 to the 4.9 K compared with 10 to the 5.2 K. They don't take that into account. So basically that's put in language like this, which is based on, is sensitive to temperature and density, a given line. And they basically don't solve for these things that are delta functions in A and B, but it determines that. And here are some measurements. That's the curve they've used. If you use some fraction of whether there's more material or less, you get either an answer here or there, and you read off a different density. Furthermore, if you solve in terms of one density, you find that everything below this line is compatible with the data. So the assumptions determine what you get, not the data, to a huge degree. Another thing is that if you have density-dependent dielectronic recombination, okay, what am I talking about? Is this, he's just being an asshole because he's just pointing out errors in some of his work. No, if you're dealing with 10 to the 13 cubic per cubic centimeter, you kill all the dielectronic recombination for physical reasons. And if you use a temperature, if you use a density of 10 to the 8, you're going to be off by factors of several. And this is the difference between these two curves here, and is just the difference between the quiet sun pressure, this would be even lower, and 10 to the 13, and this is the difference between LTE, so it's gradually approaching LTE here. This is one with no dielectronic recombination. So we're in between here, and here we are. And here's the case of full LTE, where you've got electron conversion to control everything. So basically, two things. One is the silicon line gets stronger at very high densities. The oxygen line gets weaker for the self-same reasons. Okay? Peter et al. Were blissfully unaware of this stuff. Okay, so I don't believe the densities are right at all, what they derive, and those are the primary things that force them to choose a high density in the chromosphere. The second thing is, what about other diagnostics they might have looked for? Free emission, thermal source.
I can immediately just write down, given the emission measure from silicon 4 and oxygen 4 that they've assumed, and compute what the intensity of that thing should be. I get something that's a factor of 3 brighter than Iris observed. This is genuinely a diagnostic under those extremely high emission measure distributions for not just continuum emission from the photosphere to the lower chromosphere, but also free emission from this plasma. And this difference is at least a factor of 3, because if there's any contribution to the continuum that's measured, this is the measured continuum here, from things like the silicon 1 absorption in the low chromosphere, and this difference will be even bigger. There are other lines you could look for in the Iris range. There is this multiplicity of oxygen 4. Okay, it's very, very weak. It's been reported in these things, but this would have been a very nice one to have looked at. By downloading a silly chlorine 1 line at the expense of this region here, it's thrown away a diagnostic that would have been very useful for it. So I believe this one would have been very good. Again, basic spectroscopy in the transition region. The bottom line of all this is there are several problems with the Resonant electron density which forces them to choose plasma that's deep down in the atmosphere, because you can't make electron densities very easily out of stuff at the top of the chromosphere unless you compress the bejesus out of this thing, and that's not what the line profiles show in any sensible kind of way that I can see. You overestimate the pressures by factors between 5 and 20, and my guess is that they came up with a number like this, and I'm suggesting that the phenomenon is occurring in very much less dense plasma in the upper middle chromosphere, which makes natural sense, because as the last speakers have spoken about, the alpha speed is ridiculously high up there compared with the lower atmosphere, where all this dense stuff is. So this is a chromospheric phenomenon. It's got nothing to do with the photosphere at all. And that was very misleading in that paper. I think that's basically a real problem. I think people will say, well, it's just a question of semantics. Photosphere. No, the photosphere is a place where at least 99% of the radiation emerges from the surface of the sun. That's the place where tau 500 is therefore about 0.1 or greater. This stuff here, tau 500 is 3 orders of magnitude lower. This is definitely not photosphere. So the ramifications of this. Basically, remember that most ionization equilibrium calculations, and essentially all dynamic ones as well, will be apply at very low densities. The dielectronic recombination is a really nasty business here. It's been known since 1972, that these are actually in the 1960s, and yes, it's routinely ignored in the literature that I see these days. You must analyze all relevant lines of continua, and then what is a photosphere? Well, we can talk about this. I prefer the physical versus the empirical definitions, because you can end up in real trouble if you're going to talk about, well, the photosphere is any cool plasma above the surface of the sun. Anyway, that's what I wanted to say, and thank you for listening.
Beware the evil bivariate inverse problem. Is that the take-home message? On top of not getting the physics right?
Do spectroscopy properly. Don't look at the things that you pick and choose to fit the model you want to see.
All right, we got questions. Steve, and then Don.
Cheers, thanks. All right, so I'm certainly not going to disagree with anything you said. So in the 60s, there was Alan Burgess showed that dielectronic recombination was the dominant mechanism at coronal temperatures, right? It's where it takes over, say, from the radiative recombination. So you're saying that this is actually important at lower temperatures as well. So is dielectronic recombination more important than, say, radiative right down there in the chromosphere as well?
In the transition region, it certainly is.
Yeah.
I mean, a recent paper by Paul the same thing for the lithium-like ions. Yeah.
Okay. Right, thanks.
One last one.
I think that work is very rigorous, Phil. I can't disagree with that. One of the two pieces of evidence that you neglected to mention, though, is the fact that we see all these absorption lines from nickel-2, iron-2. We even have evidence of molecular absorption lines in the FUV. So, this idea of stratification is a good point, and your points about empirical versus semantic photosphere. We have evidence that there's significant cool material happening above these events, and I think that was one of the basic
building blocks that Hardy made his argument off of. And so that's something that has to be taken into account.
Quantitative analyses of any optical depths or anything there. And so I would say that paper was rushed through. And personally, I would be embarrassed to be part of that because it's not, it doesn't have the rigor of an analysis. And it's unfortunate that those absorption lines, for instance, I would ask you, how do you know from all the evidence we've seen, from all the observations we've seen in other features on the sun, whenever you have an active region, there's absorption lines everywhere. I mean, you've got stuff raining out of the corona all the time. You've got prominences in these things. Pardon?
Not molecules. There are very few molecules in the corona.
No, of course, because you have that. But I don't know that they definitively detected absorption in
No, you missed the whole point of your paper. I'm sorry to disagree. And I must admit that I'm a reformed theorist and really an observer now, and I agree with everything that Don said. The point of their paper, and maybe it should have been published in Nature instead of Science, and only half the paper is Nature, right? But the point was that you have this very hot material that's being created very deep in the atmosphere. Now, if it's at a height of 550 kilometers or 500 kilometers or 475, I don't care. This is not the corona. This is the upper photosphere, low chromosphere. There's stuff happening at the base of the chromosphere that we don't understand. And this is the whole point of having a mission like IRIS that can see down to these levels and not be blocked by the Lyman continuum. So I'm going to totally disagree with you. I thought that was a great paper.
What's the difference between the Lyman continuum and the silicon continuum?
Silicon can be ionized very easily down at those low levels.
And carbon?
And hydrogen is really tough to ionize.
Which increases the number of neutrons. You can't have it both ways.
Well, but you see absorption on from chromospheric species on top of these silicon lines.
You see them in filaments all over the day. That stuff has nothing to do with this.
Oh.
So, well, I think you two should spar outside. But thanks for a very thought-provoking talk, Phil. Thank you. Careful.
Okay, thanks. Want me to?
Is it coming?
Yep. Yeah.
All right. And now Chen will continue our discussion. Jeff, do you need something?
No, I just want to run closer to the mic.
Okay. Put your mic on.
Okay.
On recurrent jets observed by IRIS and STO AIA, and I guess that this may address one of the questions we had earlier about recurrent jets. Right.
Yeah, sorry about interrupt your discussion. And hello, I'm Nehua Chen. No? Okay, I didn't find out. Oh, maybe it's that. Okay. Hello, everyone. I'm Nehua Chen. I'm going to talk about the recurrent jet observed by the IRIS and AIA. And the thing I want to show you is just on working world, because as you know, the jet you will observe in a large range of different scale, from the X-ray and H alpha and UV, of course. And you show a lot of picture that just take you some the interaction between the emergent flux and also the pre-existing flux. And as you show, there's a picture of this cartoon by Caffield, 1996, that you can pretty clear that the jet direction comes with the hot jet, and sometimes you will find a cool material that named H alpha surgeon, and that's the example show you that this H alpha surge usually come co-spatial with the dimming UV emission that show you clearly that. And the mechanism we've been talking about is basically classified in two types. One is recognition jet is driving by the magnetic tension force, and the velocity of the jet is usually the Alban speed. And the chromospheric vibration jet is driven by the gas pressure, and that the velocity of the jet is roughly the sound speed. And what you, of course, we do know a lot of different type of jet I've been talking about. And that here I show you just basically standard jet that usually have the inverse white shape that you can expect this long spare from here. And then that's usually transient, and you can see a co-alignment ejection like this. And on the base, you usually see a brightening at base. And for example, the X-ray, that you can see the bright point very clearly. And that sometimes people will talk about helical structure, or sometimes it's very simple, like straight jet. And what magnetic properties related to the jet is simple. We've been talking about and discussed also many before, that usually occurring at the mixed parallel region, and you do relate to the flux emergence, and also the flux cancellation is clear. And what we found, that the other thing that I care about the heliospheric people, that the signature that we usually find is type 3. That is usually do with the solar jet observed by corona, on the corona, and that sometimes it's a speedy solar ejected particle event that is usually sometimes occurring by the current jet. So this is heliospheric people will care about. And what Iris showed us, that simply I'm talking about this transition phenomena and its counterpart in the chromosphere. That's good. So this current jet observed by Iris is 2014 March 5th. And the white arrow show you where the place keep recurring, and that from the upper part is silicon 4, the down is silicon 2 line, and that as we know that we found that in the base of this current jet is actually the two flux constellation side, like showing on the HMI, and that is point from this diagram that. The main jet is coming from this region, and then usually then we'll see the other jet coming beside, and there's also another flux constellation side. So both of the jets propagate to the west-south side, and then sometimes it will propagate parallelly, and there will sometimes it will overlap together. And the snapshot showed clearly what we saw on the silicon 4 line, that all the recurrent jet sustain is pretty straight and brightening at best, as we expect from the standard model. And instead, the first jet is a little bit weak, and the velocity of that is roughly the 50 kilometers per second. And what we saw on the magnesium 2 line is very simple. Usually, you see the bright point very clearly, as we saw on the 1600 in AIA. That the one different thing I will show you are that except the bright point, we also show some dark elongation that co-spatial with what we saw in silicon 4 line. So this basically is to give you an idea what happened of this current jet. And we go on to the other thing that I've been shown a lot before previous presentation, that this basically tell you how the Raster scan goes. That in right-hand side, they show you the loops and the part of the ejection, the elongation of the jet, and the sleeve doesn't cross the full point of the jet. It's basically called a portion of the loop and the elongation of the jet. So I would so it's just a full sketch, and each explosion time is 16. It's a little bit long. So I will show you what happened in the loops and also jet. The first of all, complex jet is quite simple, because I think it's just what we find in the Sumer observation before, that the jet, the spectral show that very large bright shifted, that is already probably about 200, And then when because it's slit crossing like this one, so it's starting from the root of the elongation away. So to the tail of the elongation, we can see some two components that you usually see on all the jet. I just take one example of this recurrent jet. So the spectral line, just told you that this jet is complete. It's very simple, co-alignment and straight and untwisted. So so the other things I want to show is the roster also calls in portion of the loop that this geometry show you the loop. Why we care about is because it could be heated by the particles raised by the connection, so it's brightening as we expect. So I basically I take two parts, and one of them before jet, the other one after jet, and what it will be look like of the spectrum. And so when the loop brightening as we expect before the jetting, because there is got to be something else right heating that. So the roster cross from the foot point loop like toward the foot loop top. So the spectrum just show you it can be fed by single Gaussian, and usually you got as we know, it's usually have a redshift when it's very broad, and from the closer to the rooftop we can see some very long tail on both ends. So for the line profile, it can be just described by simple Gaussian fitting to point out what's happening. And after jet, everything's gone, and so the line profile show you just very simple cold brightening, and it tells you that most of things symmetric. So, okay. The other thing I want to show you that what we will compare with AIA, and that up panel, up panel is 304, and the downside is 171. You show clearly that this is the recurrent jet you already saw before, and here, as we expect from AIA, you usually see some brightening ejection that corresponding to what we see on silicon 4, but we do find that this kind of stuff, this kind of phenomenon first to jet. So I simply cut through the propagation of the jet. So we find that in the silicon 4 line, always see the jet occurring all the time. And for the rest of the AIA observation, that only saw something on the first two jets. Rest of that is very faint emission, or most of it is dark. So we think about why is that? Because we thought that silicon 4 showed the whole picture of the jet actually. So what happened? We usually find in AIA. So we go trace back a little bit, and we find that this is a place that this is a site that the current jet happened, and then we find that this dark material showed very clearly and always emerge and evolves with this this solar jet, and then we thought that this dark material actually, okay, this is a gap of data, and that this dark material is a blow up to the upper polymorphere, and then it will be occur the emission that we usually see on AIA. Why is so interesting to me? Because for the heliosphere people, we're struggling to identify the source of the Taft-Freiberg solar angelic event, and back to the source. So maybe it's one of the reasons that we don't really have confidence of find the source of what we see on in situ data. So this is ongoing work. So I will keep on to understand what's different between the AIA and what we see on IRIS. And I think IRIS give us so incredible information that could be lost in our AIA observation. And this is the summary I leave here. And thank you for attention.
Thank you. Any questions out there? Oh, we have one.
I have a question. Do you know what dominates the jet? Is electrons or ions?
Basically, it's electron.
Electron.
Yeah.
Okay, thank you.
I think in the heliospheric context, type 3 bursts in longer wavelengths are more important, not like metric. And I think your iris jets are more easily seen in metric ranges than on DH on longer wavelength ranges. That's why they didn't reach the corona. That's my interpretation.
Sorry, maybe I didn't get you right. Can you repeat the question again?
No, I'm talking about type 3 bursts.
Yeah, of course.
And the relation between type 3 bursts and the jets. And your iris jets obviously didn't reach high altitudes.
But yeah, that's the beginning of what I thought. But from the data we said, we do see some counterpart from the AIA and 171, 211, and 193. Yeah. That could be, so it says, I think, it's really propagated outward to the corona. So we thought it might be a source. Mm-hmm. So I just thought about, because I'm doing the type 3 bursts before, so I think about sometimes we will lose some information from AIA. So I'm interested to compare what happened in downfall, what happened in the log sphere to the what. Because we know we're struggling to identify source. So this is one way I want to try.
Did you check the type 3 bursts in this case?
Yeah, I do try, but sadly that we have a lot of active region at the same time, all have a jets occurring at the same time, so it's really hard to do that.
Right. I've got, Paul, did you want to ask a question? And if you can you yell it?
Did you look at the AIA 1600 channel?
Yeah, basically the same with the medication time. We saw from here that you always can see some bright foot point from the 1600. And what different showing on medication 2 lines that the extension of the jet material.
Following the previous question, is there by chance a coronal hole close to this active region?
Oh, sorry, I didn't make clear for you. This just beside the active region, just gets a private region. Just close the sunspot, and it's okay, pretty away from the coronal hole.
All right. Well, thank you. Thank you. And so that ends the session. Come back at 2 p.m. please for this afternoon's tutorials. And thank